Welcome back. We have previously discussed the energy potential of offshore wind. But one issue is the kinetic energy in the wind. Another is how much energy the wind turbine can extract. This is described by the power curve. Later, we will revert to this curve and explain why it looks like it does. Not all the kinetic energy in the wind can be utilized. In that case, we had to stop the wind. If we consider a cross-section with an area equal to the swept area of the wind turbine rotor and perpendicular to the wind speed as illustrated in this upper figure, it can be shown that the kinetic energy of the wind is proportional to the density of the air, ρ, the swept area of the rotor, A, and the third power of the wind speed, U. The kinetic power of the wind is given by P wind, shown at the top. From this formula, you will find that at a wind speed of 10 meters per second, the power of the wind is about 600 watt per square meter. A classical result is that at maximum 59% of the wind energy can be extracted. That means that the power coefficient Cp in the second equation at maximum is 0.59, or at 10 meters per second at maximum 360 watt can be extracted per square meter of the rotor. However, at large wind speeds, the generator will not be able to convert all the power available. The power output is thus limited to what we call the rated power of the turbine. A typical power curve for a real turbine is shown in the lower figure. This figure shows the produced power from the wind turbine relative to the rated power versus the wind speed U. At very low wind speeds, below cut-in speed, no power is delivered. At wind speeds above cut-in, the turbine are designed to optimum power production. That means the power production increases approximately by the third power of the wind speed until rated power is obtained at rated wind speed. For wind speeds above rated wind speed until cutout speed, the power output is kept constant, implying that we do not extract all the power available from an aerodynamic point of view. For wind speeds above cutout wind speed, the turbine is set to idling mode to reduce the structural loads. Thus, no power is produced at these wind speeds. As illustrated in the figure, cut-in wind speed is in the order of 3 meters per second, rated wind speed typically between 9 and 12 meters per second, and cut-out wind speed at approximately 25 meters per second. By combining the power curve and the wind speed statistics of a specific location, the energy produced over time at that location is obtained. Thus, the energy estimates depend on the assumed characteristics of the turbine. In this figure, I have illustrated how most wind turbines operate at various wind speeds. At very low wind speeds, below cut-in, the rotor is standing still or has a slow idling rotation. No power is produced. As the wind speed is increasing above cut-in wind speed, the rotational speed is increasing with the wind speed. Ideally, the rotational speed should increase proportionally to the wind speed, keeping the tip speed ratio constant. In this range, the blade pitch is kept constant. The aim is to extract as much power as possible. When the wind speed is so high that the power production reaches the capacity of the generator, the rated power, a new control principle is introduced. Now, the rotational speed is kept constant while the blades are pitched to secure that the power stays at rated power. Thus, the power extracted is lower than what is available from an aerodynamic point of view. In the transition range between the below rated and the above rated wind speeds, a mixture of the two control principles are used to secure a smooth transition. As the wind speed exceeds cutout speed, the blade pitch is set so only a slow rotational speed is obtained with no power production. This is to reduce structural loads on the turbine.